Hello, Mr. Collier here. We're going to talk about section 2 of chapter 4, which is all about the subatomic particles and their discovery. To talk about the subatomic particles within the atom, we first need to understand electrical charge. And to do that, I want to talk about Ben Franklin, a Philadelphia hero. And he was alive in the 1700s. And in 1752, Ben Franklin was the first person to suggest that the structure of the atom was related to electricity. He found that there were two types of charge, and we call them positive and negative. And if you have negative and negative, they repel. Negative and positive attract, hence the saying opposites attract. And positives repel. This very basic concept regarding electrical charge, what attracts and what repels, is going to be the basis for a lot of what we do with atoms and our understanding of the structure of atoms. So I want to talk next about what a cathode ray tube is. This is an evacuated glass tube, so it's almost a vacuum, where a beam of electrons flows from a cathode to an anode, or from the negative electrode to the positive electrode. This beam can be bent with a magnet, and we're going to talk about that now. So what was found was that a cathode ray tube created this beam, and that the beam was deflected by a negative charge, which showed that the ray had a negative charge. And the beam could move a paddle wheel, which showed that it was a particle, something that could actually hit the paddle wheel and transfer momentum. J.J. Thomson put this together and described that the cathode ray tube ray was actually made of electrons. They have mass and they are negatively charged particles. So he's credited with discovering electrons. He called his model the plum pudding model, where the electrons were little negative charge inside of a positive sort of gooey pudding. I'm going to talk about a few scientists related to nuclear chemistry real quick and radioactivity. Henry Becquerel in the late 1800s discovered radioactivity by working with a radioactive rock. And the basic idea is that he had this film that would be developed when it was exposed to certain things. It was a photographic film, so when it was exposed to light, it would be exposed. But what he found was that if he put it in a drawer with no light, but next to a radioactive rock, it would still get developed. This led to the beginnings of our understanding of radioactivity, which is the spontaneous emission of matter and energy from a sample. This is what exposed the film in Becquerel's drawer and left an image. Marie and Pierre Curie, also in the late 1800s, early 1900s, studied radioactivity much further. They discovered new radioactive elements, radium and polonium, and did a lot of work and won Nobel Prizes for it. This leads us to our discovery of the next subatomic particle, and this was by Ernest Rutherford in 1903. He studied under Thomson and discovered three types of natural radiation or radioactive decay. What he discovered was that alpha particles were drawn slightly toward the negative plate. So the fact that they were drawn toward negative meant they were positive, and the fact that it was slight attraction meant that they must be fairly large. And as it turns out, an alpha particle is a helium nucleus, 2 protons and 2 neutrons, whereas a beta particle was attracted largely to a positive plate, which meant it was negatively charged, and since it was drawn more dramatically, it must be lighter, which is true. This is just an electron. Gamma particles are not deflected at all. They are neutral. They have no mass, but they are the most penetrating radiation because of that. Rutherford is probably more famous nowadays for his gold foil experiment and his analysis of that. What they did was shot alpha particles at a sheet of gold foil and observed what happened on a detection screen. They found that most of the particles went straight through, but some bounced back or were deflected. What that shows is that the atom is mostly empty space, which is why most of the particles can go straight through without hitting anything, but those that were deflected, if positive particles were deflected, they must be hitting something positive. And so they concluded that there was a dense and small positive nucleus. So if we want to summarize the models of the atom, J.J. Thomson thought the atom looked like plum pudding with negative charges distributed throughout. Ernest Rutherford, after his gold foil experiment, determined that the atom was mostly empty space with a small dense nucleus that was positively charged. From there, we have Niels Bohr, who thought the atom was like a solar system, called it the planetary model, and that electrons existed in different energy levels, much like the orbits of different planets around the sun. He was on the right track, but found that was still a little too simple. Today we use quantum mechanics to describe the probability of the electron being in a certain region, and they can be in different regions at different times, unlike planets. And so here's a diagram summarizing that from Dalton in the early 1800s to what we use today, the electron cloud model. Now, along with the electron cloud model comes this idea that electrons can actually change their energy level. The energy level that they start in is called the ground state, and the higher energy level is called the excited state. And this happens when energy is added to them. However, they're unstable in that excited state, and when they fall back down to their original energy level, they give off electromagnetic radiation in the form of light. The light that is given off is called the atomic emission line spectra, and every element has its own unique fingerprint of light that it gives off. Here's an example of some different emission spectra for different elements. And as you can see, certain lines representing certain wavelengths show up in different elements, which allow you to figure out exactly which element it is. Now, there is one subatomic particle we haven't talked about yet, and that is the neutron. It was discovered by Irene Curie-Joly, who made a beam of particles that turned out to be neutrons, although she didn't know it at the time, by bombarding beryllium with alpha particles. James Chadwick, who tried to bend that beam, couldn't bend it, and figured out that this was the neutron, the neutral particle. James Chadwick's work discovering the neutron won him the Nobel Prize, and it also made possible the development of the nuclear bomb. So to summarize, there are three subatomic particles: protons, neutrons, and electrons. We measure their mass in atomic mass units because their mass is so small that to talk about them in grams or kilograms is really tiny numbers. Protons and neutrons are located in the nucleus. Protons are positive, neutrons are neutral, and electrons are negatively charged and found outside of the nucleus. We say that the electron has a mass of approximately 0, and that is just because it is so many times smaller. You would need about 2,000 electrons to equal the mass of a proton, that we've decided it's easier to just not count them. And that's where we're going to stop for this lesson: protons, neutrons, and electrons in our subatomic particles. Next, we're going to talk about why counting them is important.